Are you able to see my screen? Yes? Yes. Okay, so can I start? Great. Okay, welcome my audience. I'm Euclidean Chatterjee. This is the workshop for machine learning in solar physics and space weather. Today we are supposed to have the tutorial, the second class. Yesterday Sourangshu took care of one. So I would like to talk about data limited scenarios and answer if you can, because then I can, filter it out and tell all the online people too. Let's say everybody concentrate now on my figure. So the figure is very simple. It is for a human being. Let's say that there are two sensors which collects height and weight. So you can see that x1 is in height in centimeter and the y-axis in weight per total kg of the person. Okay. Now the blue points are random people, male, their height and weight. So you basically collected those height and weight and projected on this two-dimensional plane. Clear? And then we have these red points, that which is basically the female random people. That's the red points. Suppose that you have 50 people, that 50 total number of people, these blue and red, female and male. Now you see a star point. If you see my screen, that my cursor, there is a star point here. This star point is an unknown persons coming in. So you collected height and weight, and the computer has to tell what is the gender of that person. So it's basically simple binary classification task. The task is, given this height and weight, this new height and weight, we have to tell what is the person's gender. Previously, the blue points and the red points are all marked. You have collected it from, from the random people. So this is the data set what you had. Okay, so given this data set, this new person comes in and you have to tell whether this person is a male or female, a man or a woman. Clear? Okay. Now, how many types of classifications I can do as a computer, system? First of all, I would like to have supervised and unsupervised this difference. Supervised and unsupervised difference means when we had these points, luckily I asked them at the time of data collections, we have asked them gender. You may not have that. You may forgot that, or you may never thought that you have to ask the gender. You collected a height and weight, and then somebody is asking you, okay, the new person comes in, can you tell it's a gender? Okay. So that means when you collected the data sets, the gender was not explicit. So let's say assume everything was blue point. Okay. Then that is an unsupervised system. Supervised systems when I already have the gender with me, and then I'm asking the same question, is which gender it is. Okay. Then it's a supervised system. So your collection and your query matches, then it is supervised. If your collection and query does not match directly, then this is unsupervised. As a human being, we are very good in unsupervised learning. Computers are very bad in unsupervised learning. So far, most of the success that what we see in computer case are supervised learning. Okay. Now let's say that things are supervised. That means I know the blue points, I know the red points. I'm asking, what is the gender of the new person? What are the possibilities I can have? How come that I can design my own classifiers? First, let's say because I'm unable to draw, so my cursor is the drawing now. Let's say that I draw a line like this, one line like this. Okay. If I can draw one line like this, then that line, just imagine one straight line. So in the right side of the line, maybe this is male, and then the left side of the line, maybe this is female. That's the way I can think, okay? Then the question will be whether the line will be here or line will be here, okay? So if the line has, in the two-dimensional case, I have y equal to mx plus c, this is the equation, then what is my m, what is my c, okay? So according to that, I can choose different lines, right? The question is, what will be my line? Second question, is it a straight line or it's a curvy line, something like this? Who knows? Okay, so now imagine that I am showing you all the cases with two-dimensional feature vectors or two-dimensional data, but assume that I have 100-dimensional data, 100 different kinds of observations I got for two class problems, okay? Then you project yourself in the 100 dimension, imagine yourself, and then there will be a hyperplane. The hyperplane may be straight, maybe some arbitrary curve shape. Okay. So if I knew this curve, then I can say, okay, fine, left-hand side and right-hand side. But left and right, it also gets very complicated if you're in the 100-dimensional space. I mean, what is left, what is right? That is also very complicated. And this is also two-dimensional class problem, but you may not have two-dimensional class. Two-dimensional problems are typically very easy problems in our domain, in the machine learning domain. So maybe that you have 10 class problems, okay? So for example, you can have apple, orange, banana, you know, cat, dog, several things. And then you have to figure it out which one is it. So it's a 10 class problem. So that means that whole space is divided into 10 parts now, and one part you have to belong. So, and then how do you define which then it's a multiple hyperplanes, and you don't know how to design all these kinds of hyperplanes, right? It's a difficult problem. Then second problem. Let's say that somebody does not like this hyperplane kind of things in the imagination. It's a leader-based method. I basically in the bracket I wrote some terminologies like k-means and then leader. Then possibly it is easier to visualize. Visualize means, let's say that, yes. Yes.
What if the gender of 40% of data points is missing or forgot to collect? Or is this line the assumption that we know the gender of all data points?
Okay, so good question. So that's why that if this is an unsupervised system, then the gender is not given to me. Then somebody can ask, can you please predict the gender of each point in the training data? Okay, so that then the gender is a latent variable, and we have mechanism how to estimate it. Okay, one of the standard mechanism called expectation maximization framework. In there, you can think the gender as a latent value, and then you try to estimate it in a probabilistic manner. But right now, let's say for the sake of simplicity, we assume that everything is leveled. So you know which one is the blue point and which one is the red points. How do I go like this? Yeah. Okay. So go one more. Red. Can you see my screen? Like this line? Okay, good. Then it is much better actually. But then you have to push it like this. Okay, later. Okay, so how do I take this line off? So if I have this line, then just take a line and then think, and that's what I was telling. Now let's say that I don't want to have this lines-based method, but I want to do it in a differently. Let's say that from all these blue points, I try to find out one leader. Maybe the leader blue point is this one, and from the red points, I find out another leader. Maybe that is this one. So very simple mechanism is that I basically take mean value of all the blue points. That is my big cross. And the red point, mean value of all the red points. That is my red, big circle. And then I say that, okay, the new point comes in. New point is, this point. So this point, whichever is closer to these leaders, we belong to that class. Okay, that's the way to think. Very clear cut. This is called k-means algorithm. K means here k equal to 2 because I have 2 class classification problem. I have 2 leaders. But if I have a 10 class classification problem, then I have 10 leaders. For each class, I find out a leader, and then only 10 leaders are there. Any new point comes in, geographically, you basically, in the geometrically, you try to find out which is the closer to that particular point among the 10 leaders. Whichever is closer, that belongs to that class. Clear the method? Very simple case. Now note one very interesting thing. Yes. If this is equidistant, then basically you basically break it up. So you basically use greater than equal to relationship. Now, interesting, see that. Let's say that this, in my drawing, I have this these 2 points. That one is this is my leader and this is my leader. If you use Euclidean distance based classification, that means you basically new point comes in, you calculate Euclidean distance between this leader and that leader, whichever is the minimum one, you choose that leader as your class. Then actually that method is nothing but like this. You connect these 2 lines and then choose a perpendicular bisector. Perpendicular bisector is this one. Because I told the Euclidean distance, so the perpendicular bisector is the dissecting line, which basically tells, left hand side is one place and right hand side is another place. Got it? But perpendicular bisector is the right answer, nobody told you. So this is one way to think. Then there is another method which is very powerful, that is called k nearest neighbor. And this is called voting based method. Okay. In this case, you don't choose a particular leader. What you do is that any new, how do I take these lines off? This is the lesson. Yes. Yeah. Okay, and this one. Okay, so now let's say that I have this blue point, I had this new point, but then I have all other points. So what I say that, well, I choose several points in the neighborhood. This is my neighborhood. Okay, I choose a radius and then choose several points in the neighborhood of that region. And then I see that, okay, how many of them are red point and how many of them are blue points? For example, let's say the red points are 10 and blue points are 4. Okay. So in that case, I will say that, okay, in my neighborhood, as 10 points are red, my chance of being female is more likely. So I will choose female. Is it okay? So this choice, that how many, what if I choose a radius, then this is a radius based choice. Nobody knows how to choose the radius actually. Okay. Because if you choose infinite, length radius, that's a bad choice. At the same time, if you choose very small radius, that's also a bad choice. Okay. You have to choose in between something. Exact radius, we don't know how to choose it. There is a way to choose it by cross validation. It's just an experimental way of doing something right now. There is another one, is that, okay, let's say I choose capital K numbers. Let's say capital K is 10. 10 numbers of nearest neighbor points what I had in my training data sets. Maybe the 10 numbers of nearest neighbors are this point, like this, several points. Okay. So within these 10 numbers of nearest neighbors, maybe 6 came as a male and 4 came as a female. Then I will say that, okay, 6 is male. Sorry, the new point is male. Okay. But at that time, also k equal to 10, that's also not very clear that why you have to choose 10. Somebody can say, oh, I should choose 20 or I should choose 50. Okay, I may choose 2. So that's also you have to figure it out by the cross validation scheme. Clear? Okay. Okay. Why I told k nearest neighbor? K nearest neighbor, you see one very interesting thing. If the number of data points are low, That means, let's say that I have these total blue points are, something like 20 and total red points are 20. Let's say that you have an experimental setup in your physics or, in your science where you cannot collect lots of data points. That's a data limited scenario, correct? Now, if I have very few data points, I want to calculate a mean of that value. That mean is very unreliable, right? Because to calculate a mean, I need certain numbers of points in my hand, correct? That's what that your basic statistics says. Huh? Now, in that case, I don't want to get into these mean-based systems, like in a k-means-based system. Instead of that, I will keep the original signal or original data points directly, because that is only very few points, like 50 points. Any new point comes in and I can compare directly with them, right? And then choose which one I would like to classify. Agreed? Okay. Clear this point? Now then, probabilistic framework. Probabilistic framework is like this, that I have two kinds of data points. I say that, one kind of data point is okay. So I try to fit a distribution, a probabilistic distribution on each class. So for example, for the blue points, maybe that I try to say that, okay, this is for the blue points, I try to fit a Gaussian distribution. And for red points, I try to fit a Gaussian distribution, multivariate Gaussian distribution in this case, because these are two-dimensional, okay? And then any new point comes in, I calculate the likelihood of one Gaussian distribution and another Gaussian distribution. Whichever is the most likely, I can calculate that one, and then I try to find out which one is the, male or female. Clear? That's a probabilistic framework. So in that case, I have to know that which kind of data I'm handling, and which kind of distributions is the right one for that particular, data set, that what I have. For example, if I know that I have feature vectors which are non-negative, then maybe Gaussian distribution is a bad idea, right? Because Gaussian distribution can have a negative value. I mean, there is a high chance. So if I know that everything is positive, then maybe that I have to use positive bounded distributions, right? Okay. I can also have multimodal distribution. That means in this figure, maybe the data is concentrated into two distinct regions, but that is not the case. Let's say that you have two class problem, but you have several for every class, let's say blue points, but they are not in one region, but they are scattered in the two-dimensional space in different places. That means it's not a single mode distribution. Okay. So in that case, you have to use a multimodal distribution. Then you have to think, okay, I cannot fit one Gaussian to the whole distribution, but I can fit multiple Gaussians here and there in the algebraic space. That is called Gaussian mixture model. These are all nothing new, all standard techniques in machine learning used for last 50 years. Okay. So probabilistic framework, I have a maximum likelihood framework. I can also have a maximum a posteriori framework. I will come that one little bit later. Then there are another approach. Here you are calculating height and weight. This is man or man or woman. Now after getting this height and weight, what you can do, you can transfer that one, you can transform that one to some other variables which may be interpretable to you or which may not be interpretable to you, whatever it is. But in that domain, maybe things are much simpler to distinguish. It can happen. Okay. So for example, let's say, okay, so let's say I have a two-class problem. Let's say this is one class on the real line, and this is another class on the real line. Okay. So the cross points are one class. Let's say that is cat, and rounds are dog. Some feature I have taken, and I have the one-dimensional feature, so only one scalar feature, and that I'm those values I'm plotting on the real line. Clear? And then I'm asking, can you please have a linear classifier? Linear classifier means can you design one single line such that you can classify it. It's a very difficult problem. It's impossible to do that. Okay. But then I say that, okay, let's say the feature value is represented by X. Okay. But then somebody says that, oh, I don't only want to work on X, but I also want to take, I got X, I know the values, but can I calculate X square? So let's say this side is X square. So you see that what will happen to the X square? X square is nothing but parabola like this, right? So this value will be here, this value will be here, this is 0, this is not 0, means this is the round, this is here, this is here. Is it okay if I plot x square? Is it okay? Then I got in the two-dimensional plane this representation, and then you see that, can I take one line and classify? Okay, so you got X, but then you think how to represent, how to transform the signal such that you can classify by standard classifier, like a linear classifier. Okay. Yes.
So we transform, let's say we are transforming our thing to X squared. What was the name for the X thing again? Feature.
X is feature. Let's say the feature was color from the white to black.
Okay, so let's say we transform our feature to X square, then we get a linear classifier.
Yes.
And let's say that we transform the entire picture back to X.
Yes.
So then it would no longer be a line, right? It would kind of look, the line would get transformed, right?
Right, correct. Yes, because in the original domain, I could have, on the X, I could have, if I could have such kind of a line, if I could have designed, then that would have classified, right?
Okay, so technically we are doing the same thing, just
but using a linear.
Okay.
line. Yes, you're correct. So that what it says conceptually, from the X, I went to a dimension X and X square, right? So from a single scalar, now I went to two dimension, and in the that means in the higher dimension, I projected the data, and then we could have designed a classifier which is completely interpretable to me. Clear? So the point number 5, that means change to a new feature. You got something, but then change to a new feature. In this case, maybe X and height and height square, or color and color square. But what is color square means practically, I don't know. Okay, something, but at least something is interpretable. But if you get completely arbitrary variable which you cannot even understand who is mixing with whom, then well, that's the way we have to act. Means as long as the things work, it is fine. Okay. So you change to a new feature and then classify. So two prominent methods are neural network. If this is image as an input, then the one prominent method that which is today is very, or maybe that, fuel for machine learning is today convolutional neural network. I'm not going to teach you the convolutional neural network. And then another thing is called kernel trick. Yesterday, possibly, Shorangshu was telling support vector machine. This is the same trick. Basically, you project the data from the raw dimension to a higher dimension, and then you design your classifier. Okay. So in case of support vector machine, this is a binary classification problem, and support vector machine is optimal because this is a convex problem. Okay. Then you can have another kind of clustering, also or classification exists, that is called graph-based classification. I don't have a very nice picture here. Then what you do, you basically take all these points here, Oh. Okay. So what you do is that you take all the points and then you connect the points thinking about some relationship between each other. So all points are independently drawn, right? Because I asked the randomly people, like in this room, randomly I took, okay, Shubhadeep, your height is more. Please give me your height and weight. Okay, randomly, right? So height and weight will not depend too much between each other. So all these are independent sampling from the height and weight distribution. That's the way I've collected it. But then I try to figure it out. Maybe what is the relationship between them? So for example, if there is another tall guy in the room, maybe the Shubhadeep and that tall guy is much closer. Okay, so that is going to come. So what we do is that we connect all the points like this. So if I have several points and the other points, you basically you can design a connection graph between each other. That connection graph is nothing but a square matrix. And the connections will depend upon their relationship between their feature values. That's the connection graph. Just think it. This is also called adjoint matrix in our terminology. And then having this connection matrix, because you have 50 points with you, that is a data limited scenario, it's a 50 cross 50 matrix. And then try to find out which are the most important directions in this connection matrix. One way to find out this one is singular value decomposition, right? You know, eigenvalues, eigenvectors. So from there, you can try to find out what are the major classes in this connection matrix. Okay, so that is called graph-based clustering. I'm not getting into that one right now. Okay. Okay. So let us do simple case that I have a d-dimensional feature x1, x2, x3 up to xd, and x1 is maybe color, x2 maybe height, you know, x3 maybe temperature, x4 maybe humidity, as you like. And then for, yes, please.
Out of 5 techniques given on the slide, 2 to 6, which are supervised or unsupervised?
Okay, so all of them, when I talked here today, almost all of them were supervised, but you can use it in unsupervised mode also. Okay, because right now I have worked with all blue points and red points, which are marked. But if you are not lucky to have that, still you can use some of them in the unsupervised manner, but in the same, you know, formal framework. But
He's also asking what is K means.
K-means algorithm is when you have the leaders actually for every clusters, and then a new point comes in, you basically compare between the leaders, not with all the points. But when I have a connection, you know, when I compare with points, then this is K nearest neighbor. So this K nearest neighbor K, and K means K. These two K are different meaning. Okay, so don't mix up those two Ks. Okay, so can I proceed now? Now we have this d-dimensional feature you are seeing. For the kth class, K equal to 1, 2, 3, 4, how many classes you want for your data set, okay? So the kth class, I have a distribution Px given K. Then what I do is that, you know, this is my standard, so Px given K, and this is my standard relationship that is called map rule, maximum a priori classification rule. That is, for every class, I try to find out what is the likelihood value given an input data point and a class prior. Class prior means what? For example, if this is a man and woman case, maybe currently in my audience, there are only 2 female candidates, possibly all are male. Okay, mostly. Right? So in that case, I know that if somebody new comes in, these priori information I can use. For example, let's say 20% is male, 20% is female, 80% is male. If this I knew from my standard data set, then if a new person comes in, this is my a priori information which I use for the gender classification, right? In the very beginning. Because let's say that, you know, when a new person comes in, then there is a camera which basically calculates height, and there is a weighing machine down, and then it tells you what is the gender. Okay. So that's why that P of x given K, that's likelihood value is basically, you know, also modified by multiplying with P of k. Actually, that what I want, maximum a posteriori means what is the posterior P k given x by forming the Bayes rule, P k given x equal to P of x given k into P of k divided by P of x, right? This is the Bayes rule, correct? But P of x is basically a constant value for a particular x, and I need a classification which is the maximum of this P of k given x. So ultimately I can discard this guy. I don't need it. I can only take the numerator and find out what is the maximum value of that, and I'm done. Now this part, P of x given k, this is class conditional distribution. That means for every class, I have to know what is P of x given k. For example, if this is a man, then I have to know how the height and weight got generated. That is the generative distribution for that particular class. Okay, and P of k is the a priori class frequency. And then if it happens that you have a scenario where all classes are almost equally likely, then you do not need this guy, maximum a posteriori. You can simply calculate what is the P of x given k directly, because all pk is same. So it doesn't matter, right? If I multiply, it does not change the values. Okay, so that is called maximum likelihood value. So what are the few? If classes are unbalanced, because in your case, I have seen in many cases that this is true. For example, let's say somebody wants to find out a disease. Okay, somebody wants to find out in a cell if this is a cancer cell or not. In that case, the data that which somebody can have collected for sure will have much more cells which are not cancer, but there are few cells where the cancer exists, right? So this has to happen. In that case, this is an unbalanced data set. Okay, most of the practical scientific fields, it will be like so. So please note that you have to, when you design the system, you have to be careful about that. If we have complicated distribution, then it is also an issue. For example, I already told you that I got the data sets and I see that the data set is so complicated, or different kinds of variables which I cannot use my known distributions on the top, like Gaussian or Gaussian mixture, or binomial, or whatever, like standard distributions, like something like 50-60 standard distributions possibly are there, and which I cannot use so easily, or even though I can use it, I cannot learn the parameters of this, right? For example, if once I fit the Gaussian distribution, I have to know its mean and covariance matrix. But I found out that it is very difficult to figure it out from that data. Then I'm in a problem. Okay. And when you have a limited data case, then if we have many parameters in the distribution, that means, I know that what kind of distribution it should match, that possibly I have got from my physics or science background ideas. But what I found out that, I have to learn many parameters to fit that one. But I don't have that much of data. That means that you are basically learning all nuisance parameters, okay, bad parameters. So your parameters are very noisy. Then it's very reliable result. Okay. So I first give you an example called naive Bayes. To get into naive Bayes, first you have to understand what is Gaussian distribution, so that everybody is in the same page of me. Okay. So here I am showing you two Gaussian x1 and x2 two-dimensional feature vectors I have, and then I'm showing you two pictures. One is uncorrelated Gaussian and one is correlated Gaussian. Okay, correlated Gaussian means here what I'm trying to show by this black color is that equal probability curve on the Gaussian distribution, okay, or equal likelihood curve. So if this is correlated, then what happens? If x1 I know, I can estimate about x2, right? That correlation means. And if this is uncorrelated, means if I know x1, still I cannot estimate x2, right? So when I cannot estimate the things, that means x1 and x2 are equally spread. That's why this, all over the spread, this circular. But when this is correlated, then it is taking a cucumber shape because then the data is restricted, right? If I know my value of x1, if I know my value of x1 here, I know within certain range maybe x2 is lying, right? Mostly. Clear? That's why that in how this curve looks like. Okay. And a standard Gaussian distribution has, this is the form. A standard Gaussian distribution is a second order statistics. That means if I know mean and covariance matrix, I'm done. I don't need any higher order statistics. Okay. You don't have to memorize the equation because this is the likelihood equation. So given an, if I know my mean M and covariance matrix C, then any X I put in into these equations and I can compute the likelihood value. Done? Okay. So I already have a question here. What are the structures of the covariance matrix for the above two figures? What is the covariance matrix structure? Covariance matrix has to be 2 cross 2 matrix, right? So when I have uncorrelated, how it should look like? Covariance matrix diagonal. So only the variances will exist, right? So off diagonal elements are 0, but other cases off diagonal elements will exist. It can be positive, negative. Okay. If this is positive, then the curve, then the equal probability curve looks like this. If this is negative, then the equal probability curve will look like this. Right? Correct? Because one increases, then another one decreases. Negative correlation. But one increases and another one decreases is basically the same. Just a, use of the negative sign. Okay. Now just, okay, so now let's go. For the name-based classifier, this is heavily used across many fields. Class conditional distribution is simplified. Why should we simplify and how should we simplify? Suppose a class conditional distribution is Gaussian. That means that I have this, for the kth class, I have the mu k. Mu k is the mean of the kth class, and ck is the covariance matrix of the kth class. Okay. And I have a d-dimensional feature vector. So that means that I'm in the d-dimensional space, right? So my mean is a d-dimensional mean, and my covariance is d cross d positive semi-definite matrix. Clear? Okay. Now, if I have a covariance matrix which is square, it has to be, right? Okay. And covariance matrix is symmetric by definition. And okay, just for you people say positive definite. So if this is a symmetric matrix, then if all the covariance so if all the components of the matrix exist, that means I have assumed that this is a correlated data, and I have allowed the parameters to learn is a square matrix. So if the square matrix is symmetric, that means actually if you know the diagonal and one triangle upside, then you know the other side, right? So do you see that if d-dimensional feature vectors I have, that means it's a d cross d matrix to covariance matrix to learn. So almost for the covariance matrix I have d square by 2 elements to learn. It's a square divided by 2, right? So for example, if this is 10-dimensional feature, then it is 10 squared divided by 2. That is required kind of to learn the covariance matrix. So if d increases, the number of parameters increases by square. Okay. Anything increasing by square is not very nice. Correct? Anything exponentially increase is bad. Okay. And that's why that I wrote here. So total parameters around is d plus d square plus 2. D is for the mean. Mean vector, always you have d parameters. Okay. You can't do anything about it. But for the covariance matrix, because of this particular structure, I have at least d square by 2 parameters. But you see that the number of parameters are increasing in the square, but I have a data limiter scenario. I may not have so much of data to learn these d square by 2 elements, right? So what can I do? I basically, use my assumptions. For science and engineering, we basically do lots of assumptions as long as the things are working for us. So what we do is that I assume that my component distributions, because this is my vector, x by xd, x is the feature vector x1 to xd, and then I assume this is basically product of each component vectors, okay, each component. So that's why I write p of xi given k. Xi is I equal to x1 p of x1 given k into p of x2 given k, like this. So this is nothing but I assume that the components words are independent, okay. So the joint distribution can be write as a product of all the independent feature vector distributions. Yes. No, this is not IID. If this is independence is assumed, but not identically distribution. P of x1 given k and P of x2 given k can be quite different. Their mean variance terms can be different. Mean and variance should be same. Yes, has to be same. Okay. So here the general assumption is that I assume that the distribution, the joint distribution, is statistically independent. Okay, so each component is statistically independent. That's the way I thought. So I basically thought in the case of Shubhadeep, his height and weight doesn't have any direct correspondence, but actually if the height is more, typically the weight should be more, right? But if the feature was like this, height and color, then maybe it's perfectly okay, because height possibly does not have any direct correlation with your skin color, right? So in that case, it is okay. So we try our luck. So make it statistically independent. In that case, what will happen? That each individual scalar component p of xi given k, xi given k is a, let's say, Gaussian distribution. That means it has a scalar mean and only the variance term, right? So in that case, my number of parameters is, for each term is, one mean, one scalar mean, and one variance, only 2 parameters, right? And for d numbers of feature vectors, features I have, so 2d parameters. That's why I wrote d plus d. Is it okay? Clear? So you see that now we have heavily reduced the total number of parameters in the system to learn to 2d, which is linear with respect to d, right? 2d means it's a linear. So if d increases, the parameters increases linearly. Earlier, the parameters was increasing exponentially with an exponent 2.
In this case, covariance matrix just becomes a diagonal.
Becomes a diagonal. Yes. Okay. But please note that I'm telling you everything in terms of the Gaussian, but it may not be a Gaussian distribution. You can have an arbitrary joint distribution, and you can have arbitrary types of complicated scalar features. It can happen, but still the number of, if you made basically that by putting these independence assumptions, you have reduced lots of parameters. So the question, if we use joint model, please note that if I know the joint model, that is the best model I can have, right? Joint statistics is the best statistics what I can have. So if I knew the joint model and factored model, here I'm using the factored model, right? Because I'm assuming product. And if luckily I have infinite amount of data available, then which should be better, joint or the factored? The joint, right? So if I am fortunate to have several things, for example, I should have a lot of data. One. Second, I should know that how to model that one jointly. Second. Third, I should know the machine learning algorithm which can figure it out those parameters pretty good. Third, but that is the algorithm. Fourth, I should have the computational power with me. I know everything, but I don't have a good computer. Nothing works. Okay?
So
Yes.
there is one question. Features are often dependent, even conditional on cases. So how realistic is the assumption?
Yes. So the question is that yes, features can be dependent. That's why that I gave you this example, that height and weight. So if somebody's height is high, then typically the weight should be higher. Okay. But height and the skin color possibly do not have a direct, height and color of the hair. Maybe that do not have a direct correspondence. So this is the way to do it. For example, what I can do is that I can have D features. Some I need joint. Let's say x1 and x2 I may have a joint distribution, or x1 and x4 I can have a joint distribution, but then I assume x3, x2 and x5 are statistically independent between each other. I can assume that. Okay, that will depend upon your, your kind of your domain knowledge, that how you see your features. What is your target? For example, let's say I would like to identify let's say this is a cat or dog, but somebody is giving you a feature humidity. It has nothing to do with the cat and dog, right? So it is totally completely statistically independent thing. Possibly you even do not need to take care of that. So leave it. So several situations can come, and your choice that how will you use this product or joint between each other, it's up to you. Every added joint parameter, you are generally writing one level of square. Yes. Okay. So for example, just assume that d equal to 2, this is 2 square, d equal to 3, it is 3 square, d equal to 4, it is 4 square. So every one extra feature which is joint, you are at least going one level of extra exponent on the top. And this is the problem, because many cases I have seen the results. So the number of total data points are very low, and then they have applied a standard covariance matrix. Computer gave you, because MATLAB or Python do not understand that, it gave you something, and your results are practically very bad. Okay, but you cannot even understand this one. The problem is that you never thought about, oh, I have this much of data points with me. That means I even cannot learn so many parameters. So that's the thing that I'm doing wrong. Okay. How much time have I gone through? How long I'm supposed to speak? How long I'm supposed to speak?
You have exactly like 5 o'clock.
Hmm.
But we started late. Yeah, we started late, so maybe we can add some more time to that.
Yeah, okay. So now let's go to principal component analysis. This is one of the standard system that which we typically use for dimensionality reductions of the features one, and for better visibility, okay, or visualization. So what is that? I will try to explain you that what is a principal component analysis. And you have seen possibly this name many places. Please note that this point of time, I do not need explicit supervised or unsupervised assumption. It's an unsupervised method. In this way you think, okay? So what data points, xn, n equal to 1 to n. This is my data points I have. Every xn is d-dimensional or 10-dimensional, 100-dimensional, whatever, okay? So I got this kind of several data points with me. Capital N numbers of data points I got. Capital N maybe 100, maybe 1 million, whatever, okay? Now, just for the sake, assume that the data is mean removed. So there is no mean inside it. So first I would like to do a covariance of that. Covariance is expected value of x transpose. Everybody knows that, how to do that. That is, if you write in a sample way, that is nothing but this one, 1 by n equal to 1 to capital N, xn transpose. So xn is one vector, same vector transpose. Okay, for example, let's say the vector was 1, 5, minus 6, 7. Then this is also 1, 5, minus 6, 7. I take these two, I take an outer product, that is this xn transpose. And this is for the nth point. and then I take all those outer products, sum it over all of them, and average it out by 1 by n. Okay. If you do an average of 1 by n, covariance, okay, this is a little technical word, then this is an biased estimator. If this is unbiased, then this has to be 1 by n minus 1. If anybody understands this terminology, biased and unbiased from statistics domain, possibly that guy or have understood that what I wanted to say, but no need to elaborate more. Assume that n is reasonable number. So if n equal to, like, let's say 100, 1 by 100 or 1 by 99 are similar number. Okay. Now covariance matrix is positive, symmetric, and positive definite. So clear that how to calculate a covariance matrix, I mean how to write a code, so that if I give you some data points, some dimensional data points, how do you find out the covariance matrix? It is clear. You can code it. Correct. Yeah, I mean it's okay. By n minus 1, you don't get a bias term, and by n you get a bias term. You don't need to think about that right now. It's not required. Okay. So now this slide is very heavy. You have to give lots of concentration on this slide. I will tell a lot of things in this slide actually. Okay. So let's say that I would like to generate a Gaussian source. Maybe that I should say it in the other way around. Let's say that I give you some data points to you, and then you would like to fit a Gaussian distributions on the top. Okay. Then after that, that data points that which I give it to you has no value anymore, because once I learn my Gaussian distribution, then that data point is no more required, because then I will use that Gaussian for my maximum likelihood classification or some distribution modeling somewhere. Okay. So then I don't need that points anymore. Okay. The question is that there are several questions can come in. Is that once I know the Gaussian distribution, is this a good distribution to fit in? That question I can ask, right? Once. Second one, if I give you a new data point, then is this part of that good distribution? That means that if this is somewhere in the tail of the Gaussian distribution, maybe you say that, oh, this is an outlier. It's not a good one. But if somewhere it is in the mode region where it is giving a very high likelihood, then you may think that, okay, this is a good point to use, right? So Gaussian distribution is a generative model. What this means? That means if you say, or if I ask you, please give me a Gaussian data point with a certain mean and certain covariance. So I tell you mean and covariance. Can you please give me a Gaussian data point which is coming with that particular mean and that particular covariance? So how do you generate such kind of data points? Okay. Because once I know the Gaussian distribution, then I can forget about the true data from where I have learned the things, right? The true data does not match, does not require any more, because the model distribution, the Gaussian, is the statistical characterizations of the true data points what I had before, right? So once I know the statistical characterization, then I forget what was there, what is the true data I had. Now the question is this: having a certain arbitrary mean and certain covariance, I'm asking, can you please generate a several numbers of Gaussian points from that Gaussian distribution? For example, if this is a random number generator, Gaussian random number generator, it's a zero mean, unit variance. You can generate as many numbers of points as you want, right? But for a certain mean and certain covariance, how will you generate number of points? Okay. Correct. Yes. Shift one. Yes. Yeah. Yeah. So let's see that how it happens. This is in the left side. This part is the, let's say, two-dimensional. We can easily visualize. So I have drawn everything in two dimension. I cannot draw in higher dimension. So I have Z1 and Z2. This is Z1. This is Z2. Z1 and Z2, let's say this is my Z two-dimensional source, which is coming from n0, I, that means mean is 0 and covariance matrix is identity. Okay, so covariance matrix identity means both variances are same and off diagonal elements are 0. So this is an uncorrelated Gaussian. This is also independent and identically distributed. Okay. Okay. And then I want another Gaussian distribution. This is that is the feature vector X, which is coming from n. N is the Gaussian distribution, mean M and covariance matrix C. And this mean and covariance matrix I have told you, or you got it from the true data, whatever. Okay, you know that. So I have to generate my X, two-dimensional X, which is coming from this mean and this covariance. So what you do is very standard stuff. Covariance matrix is symmetric and positive definite. Okay, this is by its virtue. Okay, this is by its definition, how it is defined. Then, if there is a positive, definite symmetric matrix C, any matrix C, then you can do a singular value decomposition U sigma U transpose. That is U sigma U transpose. Everybody can recall singular value decomposition or eigenvalue decomposition. Okay. So general singular value decomposition is that if I take a matrix, then I can write U sigma V. Okay, U and V are two orthonormal matrices. Sigma is the singular values. Okay, now the number of and sigma is a sigma. Some values, everything is 0. Some values are only positive. Okay, non-negative. So those positive values, if I count it, that is the rank of the matrix. Okay. So in case of positive semi-definite, if it happens, symmetric positive semi-definite, then instead of U sigma V, it will be U sigma and V will be U transpose. This is a rule. Okay. You don't need to know that why this rule came. It is a standard algebraic formulation. So, and U is an orthonormal transform. That means U transpose equal to identity, or U transpose U equal to identity. This has to hold. So, on the U, what are the columns? Columns of the U are the singular vectors. Singular vectors, and diagonal elements of sigma are the singular values. Let's say they are ordered. That means highest singular value is the first diagonal one, second diagonal is the second one, like that. Okay. So what are those? Those are nothing but the singular values are nothing but basically the energy towards the Gaussian's main direction. So for example, in this case, this is the direction where the maximum energy exists. This is the direction which is lower energy. Okay. So because of this energy, it basically gets this, this shape. Because if they are all equal energy, then they will be, uncorrelated. Got it? Okay. So this is U sigma U transpose, as sigma is a diagonal positive, diagonal element, diagonal matrix, and its positive values exist, all positive. I can write this sigma to the power half and sigma to the power half. Sigma is nothing but looks like this. Sigma equal to, let's say in this case 2 dimension, maybe the first element is 2, second element is 6, this is 0, 0, let's say, just for the sake, or maybe this is minus 1 and this is also minus 1. Okay, just for the sake. So sigma has to be 0. Sigma is the diagonal by definition. Okay, sorry, sigma is 0. Okay, so these two are 0. Okay. And then sigma to the power half, sigma to the power half is nothing but 2 to the power half and 6 to the power half. 0, 0. Clear? 0 to the power half is also 0. Okay. Yes. So diagonal. So every component is diagonal. Note that if sigma, any sigma which is diagonal, and if I take sigma to the power half and into sigma to the power half. Do you see that I get the sigma itself? Because diagonal multiplies with diagonal. Okay. So no problem. I got that. So I can write u sigma to the power half, this part, into sigma to the power half u transpose. Is it okay? Okay. Now little more math. Then this u sigma to the power half. Okay. You have to know one standard rule, that is any matrix into B, if I take transpose, this is equal to B transpose A transpose. This is the standard. Okay, in the matrix multiplication. So can I write this sigma to the power half into u transpose equal to u sigma to the power half into transpose? Because u sigma to the power half transpose, this part, only this part, u sigma to the power half transpose equal to sigma half transpose u transpose, right? But sigma half transpose, sigma half is nothing but a diagonal element. It's transpose itself, right? So this holds. Is it okay? This part holds. Clear? This guy. So do you see that the covariance matrix I can write u sigma to the power half and u sigma to the power half transpose. U is the u column vectors are the singular vectors, and each singular vector's corresponding energy is properly kept into the diagonal elements of sigma. Clear? So what is the algorithmic step for generating such kind of a Gaussian? This Gaussian is like this. Draw source G from this distribution. Okay? Draw. So one standard Z you draw. That's a random number generated from a random number generator. Then generate an intermediate Gaussian random variable y equal to this u sigma to the power half into z, because because I told you mean and covariance, so from the covariance you did the singular value decomposition and you calculated this u sigma to the power half. You can, no problem, right? So this is a matrix in your hand. You can calculate and then you pre-multiply with that matrix G. Okay. By doing this, what you did in a matrix multiplication means what? A matrix multiplication is nothing but rotating the vector, right? In the algebraic space. So you basically rotated the vector according to its energy, u sigma to the power half, towards the directions of the singular values of vectors of u. Clear? Towards the columns of u. Correct? Yes. So now we are going towards this is nothing but, once I do that, what is this? This is nothing but, this y is nothing but the linear combinations of the columns of u, where the linear weights are basically these values of the z and sigma to the power half together. Correct? It means, is it okay? Okay. So version of the z and created an y such that y is towards the most dominant singular vectors of this covariance matrix what I wanted. But then still I'm in the zero mean region. So what you do is that after getting this y, you basically translate this intermediate vector by the mean vector. That means you do y plus this mean. Then it goes to the in the algebraic space towards that mode region where because for the Gaussian distribution the mean vector is the mode. Just think that in the mean vector region, that the probability distribution, probability mass is the maximum one, right? So that is the mode itself. Correct? So you basically translate this this intermediate vector y to that particular mean value, such that now that translated vector is basically one sample coming from this particular mean and this particular covariance. Is it clear now? The whole thing. Now the other way around. Okay. Now I ask you the other way around. That means I'm asking you, I give you this distribution, this correlated distribution. Can you please go back? That means I'm giving you this distribution n mu c. You got data points, few data points. You calculated the mean and you calculated the covariance. You got this one, these two, right? But that can be arbitrary anywhere. Arbitrary covariance structure, symmetric and positive definite, and its corresponding mean. So what you want to do, you want to come back to, let's say by transformation, to the domain here. You can do that, right? Because what you do, you basically find out the covariance matrix, right? You find out U sigma, these kind of things. You multiply U transpose, then this will be uncorrelated. Then you take the zero, corresponding mean out. It comes here. Is it okay? Clear? Or you can first do, you take this whole thing, you take the mean out, so it comes here like this, right? You move, right? And then you basically uncorrelated it by corresponding U, so then it takes the structure. Clear? Okay. Now imagine yourself. I will come later also better formulation, but imagine yourself that you are in a higher dimension. That means your original data dimension is 100, let's say here. So you are in the 100 dimensional second order statistics, mean and covariance exist. But you can't visualize this 100 dimension and think your scientific things. You want to restrict it, let's say to 5. Question is that how do you transform this 100 dimensional vector to dominant 5 dimensional space such that you don't lose too much information about the 100 dimension. So what you do, in the 100 dimension, you find out the covariance matrix, find out most dominant 5 singular vectors, right? And that you can calculate from the covariance matrix, singular value decomposition. You also know which are the highest variances of the highest singular values. Corresponding to those singular values, you also know which are the highest, which are the singular vectors, right? Choose those singular vectors and then project this 100 dimensional space to this 5 singular vectors, right? So that is nothing but you basically take those column vectors, you transpose those 5 column vectors, multiply with the y or the data that which you are seeing. Done. Then that means this projection from the 100 dimension to the 5 dimension did not lose too much information in the sense of energy, but you have cut down to 100 to 5 dimension. And then you are trying to visualize that 5. Got it? Now let's say that, so what is this process? This process is nothing but I have this 100 dimensional feature vector and I pre-multiply with the singular vectors, right? Such that it comes to this 5 dimension. Question is that, let's say my feature values were, height, weight, skin color, blah, blah, blah. Whether Shubhadeep has a spec on or not, whether his voice is good or not, like that. Several things exist. Okay. I'm just taking him as an example. So not for pulling his leg. So, all these things are there. And then you have projected this one to the 5 dimension using a matrix. But what those 5 dimension means practically, because everything got mixed up, right? Because if a matrix I multiply with a vector, that means the output what I'm getting is nothing but the linear combinations of the columns of that matrix, where each one is the scalar input, right? So those 5 dimensions which I got, what exactly that means physically, it's difficult to interpret even for simple linear transform. Okay, there are a lot of issues that for neural networks or other complicated machine learning methods, we have very bad interpretability. This is true, but even in case of linear transform, when the things got mixed and the feature vectors are different, if all the feature vectors are image pixels, then it is easy. Fine, I understand what it is. But when the feature vectors are different kinds of quantities having different dimensions itself, okay, one is weight, one is length, then if I once I bring them as a mixing linear combinations even, then still I have a problem to figure it out what the meaning are. Okay, so always this interpretability does not make a great sense. As long as I can use this 5 dimension and can understand something or my required things about it, I'm happy about it, let's say. Okay? Okay. So this principal component analysis is a dimensionality reduction problem. From 100 dimension, I want to come to 5. I want to come to 2. For example, in medical cases, doctors even have lots of difficulty to visualize high dimensional data. Doctors are not, very used to the mathematical ways that how we are trained, right? They are typically life science people. So, but they see different kinds of things from the patients, and then they want to have clusters. Okay, this is a disease case, this is a non-disease case, not in this very high dimension. What they want to do, they want to cut down into 2 dimension, and then they want to see different kind of patient cluster. That's their visualization. Otherwise, they are completely clueless. If you talk about 10 dimension, they don't know how to act on that. So PCA is a dimensionality reduction method. Let's say I have an X is the input. I want to get the same X back. Then this is the identity matrix, right? So if I multiply with an identity matrix, I get the same X, correct? Now let's say I generalize the scenario. Generalize is this. I have an X, then I go to Z. Z is my intermediate variable by a matrix A. So I multiply a matrix A and I go to Z. And then if I want to get back X, then I can take an A inverse and come back to X, right? If A is full rank square matrix, correct? If I do this one, then this process does not lose any information about X. I can exactly get back, right? Okay. So here my constraint was this: the dimension of Z equal to dimension of X. It has to be. So the intermediate variable, that what I saw, the Z, that did not reduce any dimension. If you allow 1 dimension reduction, just by 1, let's say that X is 100 dimension, I want to reduce by 1, then my invertibility is gone. Okay, mathematically everything is completely ruined up. Okay, but let's say now my further extension is this: I have an X, I want my Z to be smaller, strictly want. Okay, for example, I want Z is 10 and X is 100 dimensional, but I want Z equal to 10, dimension of Z equal to 10. Okay, this is my strict requirement because I cannot or I don't want to interpret more than 10 dimensions. Got it? Okay. Then I need an A. So from X, it's a linear transformation A, that which goes to Z, and then a linear transformation B, which goes to Y. Clear? And what I want, but which kind of A and B I have to choose. So what I want my X minus Y, let's say, Y is the reconstruction from X, right? From X to Z I went, and from Z I came back to the same dimension of X, that is Y. But as my dimension of Z is smaller, so I may not get back the same X, right? So what I want, let's say that I want in the L2 norm sense, okay, that I want this difference X minus Y square, L2 norm, okay? Everybody understood this L2 norm, I believe. That one I want to minimum, and I want to find out that A and B in this process for which this whole cost is minimum. Clear? The optimization problem. So I want to find out what is the A and B such that my Euclidean distance between X and the reconstructed version of X, that is Y, that one is the minimum one. Clear? In that case, if you average it out, this minimum for several X and several Y, A and B is the outcome of the PCA. That what I did before. I'm not showing you the formal theoretical proof, but actually this is the main optimization problem. Okay? PCA is one way to do that. There are other alternative ways to do that. Please note that instead of square, PCA is not the answer. Okay? Or 1, I can have different norms, right? I can have a weighted norm. I can have many things. Many ways that I can, many ways we can compare between the original signal X and the reconstructed version of it, Y, right? So if I choose my, these norms or the optimization criteria, that's the answer. But for this particular problem, PCA is the answer. Yeah.
So what is the relation between dimension of X and dimension Y? Are they same?
No, yes, otherwise I cannot compare a norm kind of a thing, right? Otherwise I'm in a problem. So here A is the reduction. So that means A matrix has to be a fat matrix. Its number of rows are lower than the number of columns. And number of columns is the same as the number of dimension of X. On the other hand, B is a tall matrix to go back to the original domain. Clear? So in this way, you can reduce the dimension problem. So PCA steps are this. You compute the covariance matrix of the X first, then you take the singular value decomposition. Your computer can do that. U sigma U transpose. Then transform the signal X, Z equal to some U transpose X. Okay. Z is still, according to my algorithm, Z is still having the same dimension of X. But this is nothing but if you take the first few, most important, let's say 10 important singular vectors, then you are basically taking some portions of the U, not the whole U, not the whole U. That means algorithmically nothing but first 10 values of the Z. So that's why I write in the fourth, take a reasonable upper portion of Z, whatever you want. Okay, assuming that the singular vectors are sorted with respect to the singular values. That means those are the prominent, directions where the most of the variance or signal energy. Signal energy is basically statistically means variance. Okay, in this way it is sorted. Clear? What is the algorithm? And note that Z is typically uncorrelated. If underlying distribution is Gaussian, then Z actually are components are also independent if underlying distributions are Gaussian. Okay, if X was Gaussian, then Z components are also independent, statistically independent. But your X may not be Gaussian. It can happen. But you want everything with using the second order statistics. So then Z components are not independent, but they are second order correlation wise, linear correlation wise, that is completely gone. That you have uncorrelated. Second order correlation you have uncorrelated, but not the higher order statistical terms, statistical correlations. Okay. Now I did a simple math to show something. How do I prove that the covariance matrix of the Z, because that is the second order correlation, is diagonal? How do I prove that? So if you do this one, using this feature reduction method, Z equal to U transpose X, once you did that, Z will be the covariance matrix of the Z will turn out to be diagonal. And that's very good, because in that case, what will you happen? At least that if you believe in the linear correlation term, you can take each component of Z, right? Z1, Z2, Z3, you can see them independently. You don't need to see them, visualize them, all of them together, right? Because everything you assume that they are at least linear correlation is gone. But how do I prove that if I do this one, that the covariance matrix of Z is diagonal? Yes.
So can we get the data back from principal components to know the most prominent feature?
Data exactly you cannot get back, because the other some principal components, if there are energies, smaller energies, you have lost them. You have not taken care of them, right? So you cannot get back the reconstruction data y equal to X. You do not get back. What you get, yes, you will get this one. That's what I wrote it here now. Mine. You will get X minus Y. This L2 norm is the minimum one. That you will get. Okay, among all possibilities of the choice of the Y, this L2 norm will be the lowest one. That you will get. Okay. Okay, so let's do the simple proof. Okay, so covariance matrix, everybody can follow this one. That this is small, no? No, or is it correct? It's correct, right? Yeah. So you can check that covariance matrix of Z equal to the expected value of Z transpose by definition. Okay. What is Z? Z is U transpose X, right? That's the way I have defined. So can I put it the expected value of U transpose X, U transpose X transpose, right? Is it okay? Okay. I have, this is a type. Okay. It does not exist. This guy does not exist. Okay. Now check one thing, that expected value of U transpose X. So can I write expected value of U transpose X here is fine. U transpose X whole thing transpose. I already told you this relation A B transpose equal to B transpose X A transpose. So can I write X transpose U transpose transpose, and that is equal to U? Is it okay? Up to this much is okay? Correct. Within this, what is the random quantities? Random quantities are X, but U is a deterministic thing, right? This is defined. So can I take from the expectation the U transpose out and U out? So this is okay. E of X transpose. Is it okay? Okay. U transpose CU. Is it okay? Got it? So covariance matrix of Z equal to U transpose CU. You got it? But what C was by definition U sigma U transpose, right? So I have U transpose C equal to U sigma U transpose into U. Is it okay? Clear? Okay. But U is orthonormal transform. So U transpose U equal to identity. U transpose U equal to also identity, right? So this guy. So can you see that now it is identity into sigma into I. So this is only sigma. Got it? So the covariance matrix of Z is diagonal, and its elements are also, ordered. So you can now, if you think that okay, I am not so much bothered about nonlinear correlation terms, at least only the linear correlations term or the second order correlations term. That means I got the components which are second order correlation removed. So I can check at least in this sense the components one by one. And I know which is the highest component, which is the second highest component, like that. Got it? So if you have, let's say for certain cases, you have an image and the image is very difficult to interpret in the very high dimension. You want to cut it down. So let us cut it down to 50. Now you know how to cut it down to the 50. Okay. There is one catch though. There is one catch. The catch is this. I have to have a very high dimension. I already told you that I have covariance matrix has D square by 2 elements, right? If D is very large, then this covariance matrix learning is a very difficult problem, right? Now go back to my slides. Here, this was my data points, total number of data points. This was my total number of data points, right? Capital N numbers of data points. Each data point was d-dimensional long, right? Okay. From there, when I write the program calculates the covariance matrix in this manner, right? Clear? Okay. Now I have a questions to all of you. At least how many data points N I need? At least how many, so that at least the covariance matrix can be defined. Not good estimate. At least that can be, that is not undefined. Can you tell? Can anybody tell me this one? What should be the capital value of the N if every xn is d-dimensional? Then what is the minimum value of the N should be such that the covariance matrix at least is defined? Any idea? Okay, I'm giving one clue to all of you. There is a rule in algebra that is rank of AB, rank of AB is less than equal to minimum of rank of A, comma, rank of B. This exists. Now can you tell anything? Okay, so I'm giving you the xn transpose is nothing but multiplication of two matrices, right? Xn is one vector, xn transpose is another vector. A vector has the maximum rank 1, right? Vector is basically the smallest form of the matrix. Just think like that, right? A vector has rank 1. So xn, so if I multiply two vectors, that means the rank is 1, right? Okay. Now I have several rank 1 matrices which I'm summing up. So what I have, at least D matrices I need such that the rank will be D, right? Correct? So if capital N is not equal to, capital N is at least not equal to D, I cannot even have this sum, this whole thing, the rank equal to D, right? And the covariance matrix has to be rank equal to D. Otherwise it's not even defined. So if my N is, if I have number of data points which is lower than or very close to the dimension, then you have a difficulty to calculate the covariance matrix. Okay, sometimes even if you cannot define it, forget about its statistical regularity and other issues. Okay, clear after this much? Okay, so Subhadeep, should we give you a break or should I continue? Okay, so I can continue. I think then I can stop and that can start little 10 minutes later. Okay. So now what previously we did, what I had is that I had all the feature vectors together and then I transformed all of them to make it to smaller dimension. Please note that we have not removed any feature vector. That we did not. Okay, we did not check whether some feature vector is more, better, or some feature vector is bad, or some feature vector is even problematic. That we did not do. For a problem, for a setup, we collected the data points, and in the data points, whatever the feature vectors I had. Okay, I may have luxurious feature vectors, I may have very simple feature vectors, whatever I have, because you can have feature vectors which basically is called, let's say those values are coming from sophisticated instruments, which is very costly or very difficult to do. Maybe that it takes days to get some features. It can happen, right? Or some of the things are maybe very easy to collect. It can happen, right? Or some of the things you collected maybe nuisance. That also can happen. But nothing we did bother about. We had the whole thing and then we interpreted, oh, I can't see all these things together. I have a difficulty. So let's cut down to smaller dimension and then interpret them, right? That's what we did, correct? Now the thing is different. Now the idea is that, okay, I have collected, let's say 100 of them, but maybe I want finally 10 of them may be useful. Other things I do not want. Got it? The difference? So it is not that I'm transforming them to smaller dimensional 10. That I'm not. I'm trying to remove those feature vectors which are not very important for me. Or this 100, I'm trying to figure it out which are the most important feature vectors for me. Okay? So you can do this way that, oh, I find out first which are the most important feature vectors, let's say from the 100 maybe 50, and then I use those to do a PCA to go to another 5. That you can do. But that is not the same if I take 100 and then directly project it to 5. Got it? These are completely two different mechanisms. Okay, you can get completely different results out if you choose this way. Okay. So let's say feature or variable selection. Often we face this question. We have many different kinds of observations or multimodal data in our disposal. You can have, for example, some cases you can have an image data, video data, sound data, you can have different kind of physical things, etc., genetic data, all kinds of things. So that's basically multimodal data in our disposals. Which variables are important for a task? That's what you are asking. And there are many ways. We restrict for this particular tutorial to a setup such that we can use convex optimization. There is a reason that why I need it. Okay, I just did not wanted to tell you, okay, do this. There is a reason. You should also realize why you want to do that. Okay, so that's why that I have to prepare a little bit to you people. Now let's say feature variable selections in a linear setup. Linear setup means what? I have, let's say, p dimensional feature x1 to up to xp. I have p different features. But let's say the output or the thing that which you are interested, okay, the inference, what you want to do, that is my output. This is actually dependent on q variables out of these p variables. Okay. But how do I know that which q variables? This problem is extremely difficult because this is a combinatorial problem, because you have to choose q variables out of p. For example, let's say a genie tells you q equal to 10 and p equal to 100. 100 feature vectors you have computed, sorry, you have access to, 10 you want. That is basically you have to choose 10 out of 100, right? That's a huge number. Even computer cannot even compute it. So forget this problem, how to solve it. Okay. So this, in the case of feature selection, for example, let's say, so for I give you, some arbitrary example. For example, people's happiness depends on temperature. At least in Sweden, everybody talks about weather. We are always dark. Okay, unfortunately. So if somebody's day is sunny, then you definitely should not be in the lab. Okay, you should go out. So depends on the temperature, let's say humidity, sunlight, food, knowledge, politics, pollution, education, friends, etc., etc. But which are important, variables? People's mood or happiness. It's a very difficult question, actually. I mean, first of all, you don't know how to, define happiness, how to measure it. And even though you can measure it by some activities, but still how to connect with all these different kind of things is a very difficult problem. And these kind of different problems exist throughout, many scientific fields. For example, I was doing something with Alzheimer people and dementia guys. You know that when we are old, almost all of us will suffer in some stage of our life. And then they test it out that what is happening, what is the stage, okay, or what is the survival chance, what is the, most likely few more years you will be better, and after that it will deteriorate badly. Okay. And these are very important medical questions, because in this way they will try to figure it out, your chance of success to survival, and also that what is the support you need to estimate that one. Because a large number of people, suddenly if it happens that within 6 months they are suffering in a high level of dementia, then the government is in a difficult problem to give them support. And then they want to connect these kind of things with different kind of things, like how they are stepping their okay, how their hands move, how their legs move, what kind of things they can read, blah blah blah. And this is a very difficult problem I found out. In the last 6 months I tried to work. It's a horrendously difficult problem. Now, creating a data set. Data sets, you see that now I have two terms, T and X. So T is target. Okay, target means that what I want to infer. Okay, it can be a classification, it can be prediction, it can be, for example, what will be the value of Indian rupees tomorrow. X is my different kinds of observations, and for the sake of easiness, I have assumed this is a linear model. That means T tilde is the estimate of the target, which is a linear transformation of X. This is the easiest way to handle. If you tell me non-linear transform of X, you have to stay with me for quite a long time to understand how it works. Okay, just assume that this is a linear model. So your actual, this is the true target. True target may be the actual value of the Indian rupees. Let's say that is the true value. And this is the thing which I could estimate as a linear model, that is T tilde. X model it, that is my noise term. Okay, clear? So this is my ax plus noise, correct? T equal to ax plus noise. So T equal to ax plus noise, this is a normal general linear model setup. For example, your base station, when it's connected with the mobile, actually use this T equal to ax plus noise. Okay. So y is the received signal, x is the transmitted signal, a is the channel matrix between your base station and the mobile, and noise is the environmental noise. You get your y, and then you try to estimate what is the transmitted signal x is. A is your channel, and channel in many cases know. Okay. Some cases you don't know. Then it is more difficult problem even. Okay. So I would like to know that which are the coefficients are most important in this x, x1 to xp. Please note that all xi is nothing but ith sample of this p-dimensional x, okay? And the corresponding target ti. These are in pair. So what I try to minimize? I will try to minimize t minus ax. This is the noise term, right? This I try to minimize, that noise square, that is the L2 norm of the noise. And that I do it for every data pair, that is I, that's why this I index is there. That is for the ith data point, okay? And I have, that's why I equal to 1 to n. Clear? This cost. So for n number of data points, I would like to minimize the modeling noise star or the fit noise star. Okay. And then I want to minimize this cost, and then this A is the optimal A star. Okay. Then any x, new x comes in, I put this optimal A star, that means here is the star, right? And I can predict for the new x what will be the target estimate. Clear? I would like to predict what will be the people's mood, or I would like to predict what will be tomorrow's humidity. I get several x. Once I get the A star, then I predict it. Okay. Now suppose that in the x, in this x, suppose that two fast variables are important variables. Let's say luckily, okay, fast two variables. It just does not, it is not any loss of generality. I just assume that, okay, the first two variables are important to, estimate the t or to predict the t. Other variables are not important. Okay. So how do you identify them? How do you, understand them? That is the question. So what will happen? My predicted target t tilde equal to ax is, once I write this ax, what ax means? Ax means A is a matrix which has several columns, right? Every column is this A1, A2, A3, like that. It has p numbers of columns, right? Clear? And I have a vector x which is p-dimensional vector x1 to xp. Okay. So I multiply this matrix with this p and calculate this t tilde. That's what I'm going to do. Now, if two variables are actually important, that means these two variables are actually important. All other variables are not important. So when I trained my cost, when I defined my cost using that data set what I have, and then I try to find out what is my A star, optimal A star, then what will happen actually? All these A3 up to A4 up to AP, all these columns are zeros, right?
So you're saying that all of the columns will be close to zero, right?
Is expected.
Is expected, but in this case, to get the values itself, we'll have to again train for all of the all of the parameters. So
Yes,
after
you are trying to learn all the values of the A. You are learning the whole A matrix. If the two most important variables are actual variables, and all other variables are not somehow connected, are not correlated with the t, which you want to know, but you have collected them, then what will happen? They will come uncorrelated, right? How they will come uncorrelated? That means their expectation between those variables and all the other coefficients are zero statistically. But in algebraic formulation, what do you expect? That these column vectors do not, have any, all these are zeros.
So then again, we would have to
Hmm?
learn for the entire A.
All columns will be 0. Yes.
So again, we'll have to determine the entire A matrix then for that.
Intermetric, because I don't know which are good. In the beginning, even I have no idea which one is good, which one is bad, right? It can happen that the x1 is good one and x5 is the good one. Then I should expect x1 column, that means A1 column, and A5 column should exist, and other columns will go to that type. Okay.
Can we consider unimportant variable as a part of noise?
Yes, it can happen. Yes. So this is the general rule. The unimportant variables will be subsumed in this plus noise term. This I expect. Okay. So right, this I told you. Right. Okay. Now I have written something. Note global optimality matters. What is this? Okay. So what I want when I have this kind of a decision to take, that some variables are important, some variables are not important. What I want to design a cost function, or I design a setup, system setup, such that whether I simulate or Shrudeep simulate, they get the same result. Okay. This is called globally optimum result, and this I will be more clear soon. Okay. What is the purpose of it? That means you need a reliable answer, trustworthy answer, which should work across different simulations. Otherwise, I get 5 variables which are important and you get 5 different variables which are important, then we are in trouble. Please note that when I had the PCA case, I didn't remove anything. I have all these 100 dimension, and then I have the covariance matrix with a general form, right? Whether you simulate or my simulate, I will get the same for the same data, same covariance matrix. I projected, I got the 5 dimension. Both of us got the same result, right? But now I have a different problem. If my understanding and your understanding are different, and we have a different kind of cost functions, which are even, let's say, okay, non-convex, I mean, it can have many different kinds of optimal points, then you may get a different result and I may get a different result. Then we have a problem. Okay, who will trust whom? Huh? This will be a convex problem right now. Right now, still it's a convex problem because it's a linear setup. Okay, that's why I told you that I'm not teaching you the non-convex, non-linear setups. Okay, to do this, there is something called sparse representation. The idea, the feature selection idea, I will try to explain it in a little bit different manner so that it is more easy to understand. Okay. Let's say we see some dense signal. Dense signal means that all kinds of data are present to you. But actually it is sparse in some basis. I will come to you to this point maybe slowly. First, I would like to have a basic primer so that you all understand what I'm talking to. First, this is the preliminaries of convex optimization. Why do we like a convex function? Convex function means a function. So let's say this is my parameter, some parameters I want to learn, and a cost, that is the optimization cost. That optimization cost looks like this. This is the convex function. Okay, that means it is and I want to minimize the cost. So this is the point where this cost has the minimum point, and this is a globally optimum cost. That means whether you simulate or I simulate, we'll go to the same cost, same value. Okay, so this is a very important thing to define, because this is a trustworthy problem. Trustworthy point. It's a stable point. Okay, so a stable point means what? If you part up the point, still it will come back to the same point. Okay, so if even though we do a mistake, we have some noisy data, blah blah blah, still we hope to get very similar point. Got it. So I wrote it even. Realize that if we part up the point, then it can absorb the perturbation. That means we can get similar results if you and me independently simulate. This increases reproducibility and leading to trust. Okay, if in this room I give you a data set and everybody gets, different features, then we have a real problem. Which one I should believe? Okay. Now, for example, if the system is this, some system, which is x equal to az plus noise, this is a linear system, linear model. And then this is also called a least square problem. If I want to know what is my z, that is x minus az, L2 norm if I want to minimize. So having x, I want to estimate about z. This is the same problem. Having x, knowing z, I want to estimate about a. Here I am saying having x, knowing a, I want to estimate about z. This is the same problem, okay? Because matrix you multiply from this side or that side, ultimately the concept remains same. Okay. Just for the sake of easiness, I am telling in terms of, earlier I was telling you that I have to estimate about a, but now I am telling about estimate about z, knowing the a. It's basically the same thing, only seeing in the other way around. Okay, conceptually. This is easier because this is the way that we generally, see matrices. Okay, so this x minus az square, this minimization problem is a convex problem like this, okay, which is drawn in. So this is absolutely important that we try to bring the things if we can in the convexity setup. Now, what is convex constraints? That's I have to tell you. What is a constraints and its role? Let us have an algebraic understanding so that you are clear that what I'm talking. Let us points, 2 observations, and we want to find or learn about 3 parameters. That's my setup. Okay. And why I have such kind of a setup? Please note that if I have lots of parameters to learn, I know that if I have a limited amount of data, then I cannot learn it. But let's say that within these parameters, I know that some of the parameters are most useful, other parameters can be 0. Okay, that also I can think. So in a data limited scenario, that makes perfect sense. So, and for ease of understanding, I'm using the linear system and convexity game. So I have a linear system x equal to az. So my first question to all of you, let's say I have this equation, x equal to az means it's the equation, right? x1, x2, and this is the whole equation. Is it okay? Clear? System clear? Now I am asking this question. I have 3 unknown parameters and I have 2 observations. Can we solve the above system? What do you think? No. Why not? Huh? So for this one, you can actually solve this problem. The problem is that you can have many solutions. All of them are equally likely, right? The same problem, that earlier I was telling that all of you get the different solutions and I don't know which one to take. It is the same thing right now, conceptually. Oh, I have solutions, but all the solutions are equally likely. I don't know which one to trust. Right? Okay. So 2 equations, that means 2 constraints. Equations are constraints, right? But I have 3 unknowns, so I don't know how to solve it. Okay. And this exactly I wrote it here. So we cannot solve the 3 unknowns. Actually, we have innumerable solutions. All solutions are equally valid. So we do not know which solution to use. No solution is a stable solution. Okay. So this leads to trust deficit. Okay, reliability problem. Now we try to regularize the problem for stability. What I do, instead of unregularized solving this x equal to az, we solve the following regularized problem. Let's say that I say you minimize the L2 norm of the z. This one you minimize because z I want to solve. You minimize the L2 norm of the z such that subject to x equal to az. X equal to az is your constraint, right? That's what you got. Clear? X equal to az. Earlier I was only solving x equal to az. That is the constraint because every z has to follow x equal to az, right? in the equation system. So I'm saying that, okay, now x equal to az I want to solve. Anyway, that is my constraint. But I want to get that z for which the L2 norm of the z is the minimum one. Got it? How it looks like? What does it mean? You see that? What x equal to the system and x equal to az. Okay, I can't draw this 3-dimension. I'm just drawing in the 2-dimension. X equal to az is nothing but a hyperplane, right? So that is my hyperplane, let's say. So all z which goes on this line satisfies x equal to az. Okay. And then I said that, okay, keep that I have to satisfy, but then minimize the L2 norm of the z. So L2 norm of the z is what? It's nothing but a circle, right? Z1 square plus Z2 square. So this is my circle. So and this is my constraint. You see that now this cuts 2 points, right? If I minimize L2 norm of the z, so it cuts 2 points. So my constraint is that, I choose that one such that it cuts the lines. So you see that some point of time, this guy L2 equal to, if I minimize this circle, it will go down, right? It will go down. It will be smaller and smaller. Some point of time, this blue line, there will be only one cut, one circle that which basically touches that line, and that's it, right? Because if I minimize, that will not satisfy the constraint. Got it? But it touches only the one point, and that's a regular point. That's a stable point. You solve it or I solve it, I will get the same thing. Got it? So variables, it should have been drawn in the 3-dimension. Got it? So in the 3-dimension, I have 2-dimensional hyperplane, and then a sphere is going down and down, and then it touches that hyperplane. That's my stable point. Clear? So I can regularize the problem using a convexification. What is convexification? What is a convex cost? Do you know? Okay. What is a convex function? Do you know that? Convex function means that I have not told you possibly. Convex function means is any function. If I take any 2 points here with respect to the function's argument is the parameters in this case, right? So function's argument, if I take any 2 points and these are my function values, at this point this is the value, at this point this is the value. Okay, yes. So if I take these 2 points and I cut it, I basically draw a line. That line has to be on the top of the function. Okay, then it's a convex function. If it is down, then that is concave function. Okay, fine. So L2 norm is a convex function. In the other way around, you can see that when I have a norm, I take 2 points within this one and I connect, that will lie within the boundary of that, because it's a closed convex function. Okay, you may not have always closed convex. Like when I drawn like this, it may be not closed in the top one, but it will be, that connecting lines will be within the reach of the function. It will not go out. Okay. For example, if I have something like this kind of thing, let's say that if I have something like this, then it's not a convex function, because if I took this point and this point, if I connect this line, that is outside the periphery of the set. Okay, then it's not a convex set. Okay. So convex function, convex set, several terminologies I am using without properly defining them, but I think for the sake of the tutorial, I don't have to be so strict, but you have possibly understood what convex means. Okay. Actually, the major reason that why I bring this convex is not for the sake of the mathematics. What I wanted to have, that you are looking for some stable solutions. Now, try to get the stable solutions as you like, and convex is one of them, or maybe the most prominent one. Okay. Now, x equal to az plus noise, I have the same system. I can do many things. I want to minimize this one. Please note that now I do not have x equal to az. I have x equal to az plus noise. Because I always will have generally noisy observations. Something. Or which is not completely linear, but I have deliberately thought it's a linear model. That's why I'm writing x equal to az plus noise. Clear? So that noise is a modeling noise. So noise I can act in two ways. One is that either model noise or the fit noise, typically. So in that case, I cannot have z equal to x equal to az. That is not a feasible solution. But what? Nothing but with respect to h, I have a circle, right? That circle's radius is something like less than equal to epsilon. That I can say. And that epsilon is the noise power. That I can say. Okay. But I need slightly more because I still have a, a problem which is ill-posed because my z dimension is more than x. Okay. That's an underdetermined system. So what I do, I minimize the L2 norm such that x minus sj less than equal to epsilon. In that case, what will happen? In that case, I don't have a hyperplane, but I have a circle that is x minus az square. And I am reducing another circle that is this Lj that will touch. These two circles will connect, contact between each other, and that is my stable point. Okay. And then it can have several versions. I can minimize the noise term such that these guys less than equal to epsilon. Other way around. I can also do Lagrangian form. Okay. Some of you possibly know some kind of definitely do Lagrangian here and there. Okay. Then lambda is the Lagrangian constant. Got it? Okay.
What if the dimension of x is 2 less than the dimension?
What is that?
What if the dimension of x is actually 2 less than the dimension of z? Because the minimization of z square mod is just one more constraint, right?
Yes.
But for a definite solution, we would need 2 extra constraints.
No, that is not true. As long as that I have a convex set, I am fine. It is not. For example, I can have 10 measurements, 10 dimensional x, and my z is 100 dimension. It's still okay.
At one point, here's how to get one stable point.
Okay, so there are issues. This is a very difficult question. For example, if I have z 100 dimension and I want to get a 100 dimensional stable solution, what is the minimum number of measurements I need? That means x is the minimum number dimension I want such that I can still get a stable solution. This is a good question. This is a very okay. That we should discuss outside this tutorial. This is a very, very difficult question. Okay, but at least this is true that when I have this underdetermined system set up, or z that which is more than number of measurements or x, then I can do something to convexify and still try to get a reasonable solution. Okay, perhaps a stable solution. Now, I have already shown you all these things, all these kind of different forms. And what is my statement? Statement is that constraint and regularization helps to find stable solutions. Please note that we have used norm-based regularization. I have only used norm-based regularization so far. Okay, there are other ways to regularize the problems. Okay. Now I tell you the sparse representation. The famous one is called lasso. Least absolute shrinkage operator is the famous one. What is like this? I assume like this. I have two equations, x1 and x2, but my assumption is that within the z, z1, z2, z3, even 3-dimension exists, but actually some of the z's are important and other z's are not important. That means there can be zeros. Okay, That means within this Z1, Z2, Z3, this 3-dimensional vector, or Z1, Z2, Z3, Z4, 4-dimensional vector, or Z1, Z2, Z3 up to Z10, 10-dimensional vector, whatever you got, within that, few of them are important. That means those are influencing to create X, because that's your model is right. Others got zeros. Okay. So if I want to solve that one, that means Z is actually sparse. This is the terminology. G is sparse means, for example, let's say this is Z. Z is a vector. Let's say a 3-dimensional vector. But maybe it can happen that Z, the first coefficient is 0. That means it doesn't have any influence. The other value is 1. That means it has an influence. The other value is 0. Okay, it can happen. Oh. So in that case, what norm to regularize? That is called L1 norm. These possibly you don't know much, but you can visualize L2 norm, but not the L1 norm. So I think that my time is coming up, right? So this is the L1 norm minimization such that x minus aj square less than equal to epsilon. I missed the point. Less than equal to epsilon. Okay, I have to have an upper bound. So you minimize L1 norm of that variable which you want to solve with the constraint, with the equation constraint, okay, or modeling constraint or model fit. And its Lagrangian form is this. What does it mean? Means how do I find out? Let's see, geographically. You will see a difference. 1 minute. Using okay. Okay. What is L1 norm? You know that when I have L2 norm, then it looks like circular. L1 norm means, for example, L1 norm. Let's say Z equal to 2-dimension, because 2-dimension only I can draw. The L1 norm is defined by Z1 mod plus Z2 mod. Okay. This is also a norm. Standard. So how Z1, if you do this one, do you see that the L1 norm looks like this? If this is Z1 and this is Z2, do you see that the L1 norm looks like this? It's not a circle, it's this one. Do you see that? Is it okay? For example, if Z1 equal to 1 and Z2 equal to 0, then the norm value equal to 1, right? That is this point. And Z1 equal to 0.5 and Z2 equal to 0.5, then still the norm value equal to 1. Do you see that? Is it okay? Clear? So with respect to the norm value, I have a very weird kind of a shape instead of a circle, because in our head the norm is always circle, but it's not true. Okay, you can have different kinds of shapes. So now on this diagram, please remove the circles from your mind. Okay, because I cannot remove that. That is already in my picture, so I'm not being able to remove that. But the constraint is the blue line. On this blue line, now I'm minimizing the L1 norm. How it will happen? It is something like this, right? It starts from there. You are minimizing it, correct? Okay. So now we minimize. Do you see that when I minimize something, then it will touch, let's say, you minimize, then it touches the constraint line, and this L1 norm minimization will touch some corner on this line and this line on the axis points. Can you visualize that? Otherwise, it cannot happen. It cannot touch anywhere else, because it has that particular shape. Do you see that? Because it has this kind of shape. So for example, here it touches, but it goes through there, but still I can minimize, right? So it can only minimize somewhere. It just touches on this line. It touches somewhere here. Do you see that? Otherwise it cannot happen, because after that, even if you minimize, then it will not touch on the blue line. That is the infeasible solution. It cannot happen, because that does not satisfy the constraint. Now, if it touches one on this line, on this axis somewhere, do you see that that means that my z1 is equal to 0 and z2 equal to something? It is going to happen. Means some solutions, some of them got to 0 because they are on the axis, or union of the axis, that is its space. This is the physical interpretation of this. So if you no, it is only one stable point.
So if the line is parallel, consider line is parallel.
That, okay, that can happen, but that is very unlikely to happen. Okay, if unless you are very unfortunate, this is not going to happen. Your line typically, that will completely parallel with respect to one side of the L1 norm. That is very unfortunate. Yes. Now think this one. This I'm doing in the 100-dimensional space, and I'm minimizing this L1 norm. That is nothing but one kind of a parallelogram, right? Which is going down and down. Then what will happen? And this has to go through union of the axes, where one point will cut through the feasible line. So what will happen? Most of the variables will go to 0. Only some of them will exist. You got your important variables. Got it? So from the 100 dimension, you possibly will wind up with 10 dimensions. You got 10 important variables to, express your target t or x, whatever. I hope you have understood the basic differences between now feature variables, dimensionality reduction, and feature selections, how to do that. Okay, I think that this is enough. So we learned in the previous slides linear method for feature selection. I have not talked about nonlinear systems. There are few nonlinear methods for feature selection in the literature, but we skip that as they are more involved. Okay, that requires lots of time and understanding. Actually, then you need training with as a machine learning guy that how to do this. Okay, thank you for listening to me.
For this lasso method, it has to be that while we are implementing L1, we have to know that only some are important, the rest are not that important. But
No, this is the automatic answer. You don't have to know that. You are trying to figure it out.
But when we minimize the L1 norm, in that case, let's say that most of the parameters become 0 for Z. But what if, they were actually not that insignificant?
Okay. So what will happen? In some cases, it can happen that you will not get, some of the values will be large. That means those are important values according to method. Some of the values will not get completely 0, but very small. It can happen. In practice, this can happen highly. Okay, so how do I stop that? Any more questions? Any more questions from the audience? Yeah, so I think that you can give 10 minutes break. We have to check that whether.
Yeah, so we will have a 10-minute break and then we will then go to hands-on session.
Do we start?
Yes, please. Yeah.
Oh, okay. So, yeah,
See,
in this tutorial, first what I would present to you are two example notebooks based on the talk that you just listened from Saika. The first one is on Lasso. And I realize that you probably have not seen much of this in the lecture, but I try to explain at least the background of what this is, and this will be rather a very simple example just to illustrate how Lasso works in practice. And the second notebook is going to be on PCA, for which I think you have had a good discussion of how it works. So first, I think both of these notebooks are available on the website of this workshop under the date of 29th of June. So in that you will find folders and files for all of the notebooks that I'm going to be presenting throughout the workshop. So like for today, as well as the ones that I will be presenting on the 1st of July. So you can download it from there, and if there is anything else required, I'll let you know. I think there you will not require to download anything else other than the files and the things that are already given in that folder on the website. So let this is actually a very simple example of where we learn how to use Lasso as a regularization scheme. So as you saw in the tutorial, that it's usually used to enforce sparsity in regression solutions, right? So here in this problem, we wish to find a vector W star that is sparse. This can be any kind of a signal. It can be an image. It can be um, like an image in if you vectorize the entire image. I mean, or it can be sound signal or speech signal and so on. But we assume that we do not, this signal is typically very high dimensional. And what we have as observations or the output of Y are low dimensional projections of this signal. So we have a projection matrix called X, and using this projection matrix X, we have a low dimensional representation of this W. And then can we still manage to uh, do this kind of a regression problem, but also ensure that we have a sparse constraint on W as well, so we don't end up using all the predictor variables. So here, as you can see, the output, so Y is your output, X is a fat matrix, which means it has more number of columns than the rows. So in this case, W will be used to solve this regression problem, and you could use the L1 regularization scheme as a regularizer or a feature selector. Certain parts of this notebook has actually been taken from an open source tutorial on Lasso. It's available on this website called scikit-learn, and I think that you have used this library already in yesterday's tutorial when you explored linear models. Um, so we have, in this tutorial, I have used the data loading pipeline from scikit-learn actually, and I hope people are more or less familiar with Python and how that works. Uh, but in this case, to give a more rather hands-on feel of how to implement such a problem, I use a optimization package called CVXPy. And this optimization package actually will help you implement this objective function and regularization by yourself. So typically in scikit-learn, there is also a library probably called Lasso. In that, more or less, the algorithm is coded already. But here you will code at least some part of the algorithm by yourself, so to get a better understanding. And in this, in the notebook, for whenever you click like on scikit-learn or CVXPy, I have provided links for resources that you can read in case you're not fully familiar of how to get started, but it's fairly straightforward to do this. So what will we do in this notebook? Basically, what we'll try to do is that we will try to code some parts of this linear regression problem using L1 regularization. There is also another optional idea to extend this implementation by using something that we call grid search. And what do I mean by grid search? It's basically trying to find a suitable value for this parameter lambda. As you saw in the tutorial, that the norm enforces a kind of square shape objective function on the objective function, right? So when you plot the w's along with the constraint on the plane in 2 dimension, it will resemble like a square, right? But of course, in 3 dimension, it becomes like a hyper square kind of thing. But the idea of here is that the degree of the regularization, the strength of the regularization is influenced by the value of this parameter lambda. And in often cases, to enforce a good um, fit to your problem or the requisite amount of sparsity, it's important to choose this value of lambda, and it can make a difference of your solution. So there is actually a very nice framework already present in sklearn, which helps you to do a grid search. That means you basically sweep over a number of values of lambda and you check the fit of this uh, objective function for every value of lambda, and for whichever fit it gives a minimum amount of mean square error. We use a certain metric such as a mean square error to measure the degree of reconstruction, just as in here it's similar, so that the lambda which will be having the smallest amount of mean square error will be the one that you need as a suitable value of your regularization parameter. And this is something that you can also do by yourself by a code, but this is a nice framework actually already present which does this kind of looping and stuff for you. And in this example, you actually see some optional code of how to do this yourself. And optionally, you can also try to experiment with some of the parameters of L, number of points, and so on. And I will explain what these points are. So if you open this notebook called Lasso Question, you'll see that at the start, we have some code cells where we import the libraries needed for this notebook. I also have a cell to print out the versions of it in case, just to ensure that you have the same versions. But in case you're doing it on Google Colab, more likely you'd have updated and nicely ready versions for your choice. There are certain.
Yeah, so sorry to
Yes.
interrupt you, but then is this possible for you to switch to the light mode?
The light mode.
Because
Okay. Yeah,
yeah.
yeah. Let me see how it will. I usually do it in the dark mode actually. I can do that, I think. Yeah. Let's see. Is this better?
Better, thank you.
Oh, perfect. Thank you. Thanks for letting me know. I usually work more in the dark mode, but yeah, possibly it's difficult to see. Yeah, so in this function, you'll see some code segments or some functions here. And some of the parts you see that I have written none. And there's a comment to insert the code here. So the idea here is that you basically implement some parts of this objective function by yourself. And this is actually not very hard because you will use the libraries. You don't have to code everything by scratch. Like for the L1 regularizer, there is a library called CVXPy, and CVXPy provides a function to implement an L1 norm. So you just have to look up the documentation and find that function and use it with these arguments so that you can get a kind of L1 regularizer term. Same for the fit error. You can have functions simply from NumPy, which computes a Euclidean distance between your vector y and the reconstructed vector that you get from x and w. And the objective function, as you can see, fit error plus lambda into L1 regularizer. So that's basically exactly analogous to the thing that I have in the equation after the arg min, you see, on the right hand side here. I have a error metric called mean square error. Hopefully everyone is familiar with it, and it's also actually exactly the fit error, but just scaled down, because the fit error is also kind of mean square error in this case. This part of when building the data and the projection matrix, uh, as I mentioned, this kind of data is actually something that I took from scikit-learn's tutorial. But what it does is that it creates an image, but it's a synthetic image. It's not a real image actually. And I'll probably show an example of how. Do I have an example here? Yeah, I have an example. So it will create actually this kind of an image, the code segments here. And I think you don't need to implement anything for the data creation part. Already everything is there. The size of your input image is going to be 128 by 128. So it's a square matrix consisting of 128 square pixels. You have a projection matrix X that I built as I explained in this equation above. This projection matrix typically consists of less number of rows than the number of columns, and the number of columns will be exactly equal to the number of pixels that you have in your image. So if your image has 128 square pixels, then W is going to be a very long vector, right, a very high dimensional vector, but X is going to be a fat matrix, which will have less number of rows and less and more number of columns. And there is functions to build this thing that we call a projection operator. That's basically the variable that is the same as X, and we multiply the projection operator with our data, which is the image, to get the projection, and this is basically a Y. So now we have a very supervised kind of setup, right? We have a Y, we have an X, we have a W. And what is the main objective of this tutorial is basically to use CVXPy to define the optimization problem. So what you do is that there is actually in CVXPy, there's a way to define W is the variable that you want to optimize here, right? So here, what we wish to do is that we wish not only solve this regression problem, but also have the sparse solution. So we have already coded our objective function. So now the only task remaining is to put this in the optimization problem framework. That we have W as the variable that we want to optimize. There's a way to define this in CVXPy. I have provided some links that you can just look up of how to do it. There are actually some examples on Lasso as well you can consult. Then there's a way to define this regression parameter called lambda. And lambda, you can initially, I have also assigned some arbitrary value. You can do that as well. That is no problem because you don't need to focus on tuning the lambda first. I would say the main objective of this tutorial would be to learn how to do this kind of process. And there's also a way to define this problem as a minimization problem. So you can try to fill up these parts of the code. Some things are left blank, some things are already implemented. And hopefully, if all things are okay and you have implemented correctly, once you run this part here, there's a way to run it by just calling this fit function. Once you run the fit function and fit your model, you will be able to visualize hopefully such a result like this. So you will have your original image, which looks like this, and then you have an image that is reconstructed using the L1 penalization, and you'll have a certain MSE looking like this, and hopefully both your images look similar. This is basically the main tutorial that I have for you today for this one. I have some other ideas also, it's like optional things to, if you want to be adventurous and play around with the value of alpha or the value of lambda as a regression parameter. And I've provided you some instructions of how to do it using GridSearchCV. GridSearchCV is a library by scikit-learn, and you can do it. Basically, you already have implemented this kind of a class for the lasso problem, and you can reuse a lot of the code to just define how to sweep over parameters and do a kind of hyperparameter search. And you can try to do the same idea and fill up, and in the end you should be able to see maybe three kinds of images. So you have one image, this is the original one, you have one which is the thing that you get from the L1 penalization, and then finally you can have one that will be the L1 penetration, but using a tuned alpha, because this alpha is now from the Gridsearch CV library. So this was your first tutorial, that the first notebook that you can look at today. There is a second notebook, and I will share that also. Let me try to do that. So there is a second notebook. For this also I have to switch to the light mode first. Do that also. Yes. So this tutorial is a bit shorter than perhaps the first one. It's just about principal component analysis. What you do here is that you try to again look at. So this is already the steps that has been discussed in the lecture today. So we basically, if we have a data set of vectors, the idea is to compute the sample covariance matrix, and from the sample covariance matrix to form an eigen decomposition, which is a crucial step. And then we we basically sort the eigenvectors in terms of the eigenvalues. And since this matrix is positive semi-definite, we can do that because eigenvalues are more or less real. And then we can reconstruct our signal from basically we have a low dimensional reconstructed signal. The idea here again as previous is to complete certain parts of the notebook, so you can form like an image reconstruction task by principal component analysis. And here I just show it using one digit. This is actually a digit dataset which is open source. It's called MNIST. It's a very popular dataset which is used in machine learning. And it's a dataset of handwritten digits. And I will show what one digit looks like. I think I have an example. So you can see one digit looks like something like this. This is a digit of a 3, the digit 3. So the idea is that this digit or this image in MNIST originally is 28 by 28 pixels. So it's a rather small image, but what we can do is that we can actually we can do a dimensionality reduction of this image. So it will be a low dimensional formulation of this one. And then we can reconstruct the image from this low dimensional formulation by only choosing the significant components or the important principal components. And that's the idea, right? We have a we obtain the principal components from the eigen decomposition of the covariance matrices related to this image. So if we collect all the threes from the MNIST dataset and form a covariance matrix, and then we do an eigen decomposition, then the first few eigenvectors will be the ones that contribute to getting this image of the 3 the most. The idea is to then take a couple of these first ones and then reconstruct my image. And we will actually see that we don't need all the 784 components. Why 784? Because we have 28 by 28. If you flatten it into one vector, it's 784 pixels. We'll see that we actually do not need all the 784 components to get a fair reconstruction. And you'll actually see towards the end that there's an exercise that when you reconstruct with different numbers of these principal components, you will get different degrees of reconstruction. And for when obviously you take only one component, you have a distortion measure. So what's the distortion measure? It's basically the difference between your reconstruction and your original. So that error, basically, that error will be very high once you take very less number of components. But once you take more and more components, that error will slowly reduce down. And of course, for this case, when you take all the principal components or all the eigenvectors, so basically you're reusing the entire image, you'll get almost a very, very low reconstruction error. And in this notebook, you'll be able to actually explore that and see. Here also certain parts only have been marked by none. Most of the parts are already implemented. And in this XPCA is, I think, the main code that you need to implement here, and the eigen decomposition. But you already have a way to do eigenvalues, to obtain eigenvalues and eigenvectors using NumPy in Python. So only the XPCA is the part that you would need to code. But this is also easy to do because you have equation that I provided here. So you just need to implement this equation where these u's will be your relevant principal components obtained from the eigen decomposition of your covariance matrix. And in the end, you should be able to see this graph of error versus the number of principal components used as a distortion measure, and also see some figures of the digits. So these are the two notebooks that I have for you today, and you can try them. What I'm not sure is whether I should let you try for some time and then probably show solutions. And I'll provide the solutions later to Shubhadeep so that you can download the solutions as well. For now, I only have the questions for you. So you can try and see how it looks, how you understand. So I think I can let you try for some time. I do not know how long is this session going to run, because we started also delayed, right? But it's an echo. Sorry, I couldn't hear you.
So actually, we need to actually we need to complete this session by 6. So maybe in half an hour
6.
maximum. So
Okay.
that
Okay.
to keep in mind,
Yeah,
because
then it's
in
okay. It's fine.
1.5 hours, we have another session will be starting. So
I see.
we need
see.
to
Yeah,
complete
sure.
by 30 minutes.
30 minutes. Okay, perfect. So I think I will then let you guys try these notebooks for around 20-25 minutes, and in the last 5 minutes I will show you the solutions for this one, and then I will provide the notebooks to Shubhadeep, and you can download and see it for yourself. And if you have any question, you can ask me in the next tutorial before we begin, so that I can try to help if possible. Yeah. So but you feel free to ask me any question during this time as well, regarding the notebooks, if there's some part which was not clear or you didn't understand. Okay. For then I will stop sharing and remain and check for questions.
One quick announcement. So if any of the participants want to share their screen or ask any questions regarding this notebook and try to show their solutions and whatever. So you can just raise your hand. We will give you the access to do that.
Was everyone able to download the notebooks at least and run them on Colab? Is there anyone who had issues regarding that? Yes, no? Any response?
So anybody has any something to show or so if no one has anything to show, then I will request Anubhav to at least explain one of the notebooks and maybe
Yeah, sure.
just explain, and then maybe in the after the tutorial we can give them the solutions, but that would be good. I mean,
Yeah, for sure. But at least like before that, if anyone has at least tried something or wherever you're are, that's also good to know. If I mean, of course, the time is not probably that sufficient for you to finish it. That I understand. But if you at least tried, that also is nice to know. So, has anyone? Did you start with the lasso one or the PCA one? I can see there are like 26 people online, but okay, at least 20 people online. Can anyone just say something? Sorry, the lasso. Okay. What did you find? I mean, you can unmute probably and just say.
No, I could not complete it. I just
Yeah.
implemented the helper functions,
Uh-huh.
and after implementing after implementing helper function, then I came to the implementation of the class mylasso,
Yeah.
and I stuck at the point wherein I need to define the value of w
Mm-hmm.
and the value of the lambda. So, but the value of the problem I initialized with the implementation of the objective function, which is so very obvious. But I was thinking about putting the values of w and lambda here, and then probably I require more time. Yeah.
No. Yeah, it's okay. Yeah, but yeah, that's perfect. I'll let me see if I can present this lasso one. Okay. So you probably have, or let me see. This takes some time to show the screen. Maybe you can see the screen now. So basically, the idea was to implement this fit error and the regularizer. As I said, it's much simpler because you are using the library itself. So it's just a matter of picking the function which will help you. I don't know, because when I share the screen, it's rather small. Let's see if I can zoom in a bit. Yeah, that's better.
I took the help of the linear algebra library of the NP
Yeah,
library, and then took the norm function from there.
yeah, that's also okay actually. But the thing is, since there there can be an issue in the sense that sometimes uh, when you use libraries with this library called CVXPy, sometimes CVXPy's variables and NumPy's variables are might clash. So it's a good idea to use the functions from the CVXPy library. Of course, the NumPy libraries would probably work as well because both are Python based, so it's not a different language. But sometimes the concept of a variable or an array in CVXPy and NumPy is a bit different. But I think for the helper functions, it should work also with if you have used a norm library from NumPy, say NumPy linalg norm, it should be still okay. But you can try this one as well. So basically implementing these two helper functions, right? The first one is just looking at we compute the two norm between x and w and y, and this notation here, this @ symbol is basically a shorthand for doing matrix multiplication in Python. Most of you are probably familiar with it. And then we have the norm 1. This implements the L1 norm on my W. And the lambda is actually the regularizer, right? The lambda is a parameter that we need to tune or regularize. So this is just using my helper functions to formulate the objective. And this was already done, right? So then this one was the main thing that I wanted to look at, you to look at. When you will solve any optimization problem using CVXPy, the problem for which you want to minimize. So in this case, we want to do argmin over W. So it's important that we define the W as the variable. So the CP dot variable, this kind of defines which is the variable or vector that we need to optimize for. Like what are we optimizing over? This is defined by using this syntax CP variable. Then specifically, if you have parameters that you want to tune but not optimize, you have to define them using this thing called parameter. That means it's then tells the solver that this is a parameter which is going to be tuned in the optimization and not optimized over. And you can actually define constraints over this as a non-negativity constraints. So this, because which is very common in case of this kind of lambdas, because it's a Lagrangian, then you might formulate it in terms of the fact that you want it to be non-negative. And then we actually have a member called alpha, and this alpha is, it's a bit redundant of a notation, but for the sake that when you define this parameter, you cannot do lambda equal to alpha. You have to do lambda dot value equal to self dot alpha. So this is the same idea as just saying that whatever thing assigned to alpha, it will be the value that is used as a regularizer here. Then comes the single most important thing, which is just formulating the minimization problem. But this is straightforward because we have something called a CP of problem, and this problem can be a minimization problem, it can be a maximization problem, and so on. In our case, it's a minimization problem. And what do we want to minimize over? We want to minimize over our objective function. And remember in the code that our objective function includes both the parts where we want to fit, that is the fit error, as well as the part using the regularizer, because we call this objective function as defined in the top. And once we have the problem formulated, we can actually solve this problem by calling var problem.solve. There is an option to set this as true or false. Basically, it means that you will see more statements as the solver is progressing. So it might be a good idea to have this as true. You might get a lot of output, but you can actually see what the solver is doing, the optimal values and so on for every iteration.
Yeah, so I
Yes.
have a query here that while
Yeah.
computing this argmin,
Yes.
where are we computing the value of argument? I mean, it's okay that we are computing the value of min,
Yeah.
but then where are we computing the value of arg?
Yeah, that's a good question. So that's basically why we define this as a variable actually. Whenever we define this W as a variable, it is implicit that this minimization will actually compute the arg mean also. So not only from this problem variable, you will have actually, this problem variable contains a lot of information. It contains the information regarding the status of the solver, whether the solution is optimal or not, whether it is converged or not. It contains the value of this arg mean also, that you actually, from this one we can get it's something that happens in the backend, but after this problem or solve is executed, if you have defined something as a CP dot variable, then that arg mean is assigned to that variable, and then you can actually use that variable here as a coefficient. So these three lines, or execution of these three lines, basically gets you the arg mean. But it's true that from the syntax itself, it might seem a bit strange as to where this arg mean is actually happening, but it actually happens in the backend, and like behind the scenes rather, and the indication of uh, over which the arg mean is happening is given by the CP dot variable.
All right, yeah.
Yeah, perfect. And then we have another function called score. Basically, this just uses our MAC function defined earlier to score our reconstruction and so on. So once we execute this, I execute this with just a very random value of 0.001. So very small amount of regularization almost. And you should be able to see that this kind of two images almost, original and reconstruction. And this is the MAC between them. There is an optional part as well that I provided to you, and it's actually very simple. If once you have found out how to construct the myLasso class, the next part is actually not that hard, because it just uses the same myLasso class, but we have to use some libraries called GridSearch CV, which I defined here. GridSearch CV is actually a standard library under sklearn, and we use something called a base estimator. You can actually, I have a link here where is a tutorial of how to design estimators and use them with search CV. But what it basically does is it provides a very automated framework for you. Instead of you coding a for loop and running over different kind of hyperparameters and running the solver on this several times, what it does is if you define a fit and a score function in this estimator class, and then just provide a list of parameters to sweep over, and you call search CV, it will do this kind of fitting for you. So it will provide a lot of fitting, and so at each time it takes one value of alpha and repeats this process, and eventually it will do what we call in machine learning a k-fold cross validation. So if you have a lot of samples, you reserve a part of it as validation and you train on the rest. So and you repeat this process in a rather cyclic manner, so that at the end you will have a suitable value of a parameter. And once you do this, you'll be able to find actually a very suitable value of alpha also that and then you find that you might have even a smaller test error also at the end by a tuned value of alpha, and you can display this later on as well. I think this is the picture that I already had, but I didn't have the other things because I just wanted you to try and solve this. And you can find what will be the best set of parameters by using this dictionary. Basically, the grid variable here contains again a lot of information about the quiz search. So what will be the best parameters, what did the solver find, what were the different kind of combinations the solver tried, and so on. So yeah, that was basically the notebook, and I will provide the solution also that you can try and see for yourself in case it's not clear.
So how popular this library CVXPY is, because I heard about this library for the first time in today's session only. I mean, I used to use
It's
now.
no, I mean it's true. I will say it's a I will not I can't probably claim that it's a very popular library, because you have analogous libraries such as SciPy, Optimize,
Yes.
Minimize, and so on, right? But what I like about this library is that it's a bit intuitive, in the sense that in SciPy also you can define your minimize functions and then define bounds for your parameters and so on. But I chose this library for this example because it provides a very intuitive yet detailed way of getting into the problem in itself and then trying this. I will say it's fairly popular, at least some of my colleagues and I use it sometime when we have this kind of simpler problem. It's a good way to get acquainted with, I think, convex programming in general. But this is a library more focused on convex optimization, especially. Uh,
Yeah, thank you.
but
Thank
yeah,
you for this. I will start using it now and I'll
yeah,
see its documentation. Yeah, thank you.
yeah, yeah, no problem. So yeah, I guess that was it for this one. I think we do not have enough time that I can show you also the PCA one, but I will. You can see the solution notebook that I will share with you, and let me know in the next tutorial if you have any question for that. But that is a much more relatively simpler notebook compared to Lasso, I think. So yeah, I think we
Okay,
are.
so yeah, if anybody don't have any questions, then please try these tutorials and maybe you can contact Anubhav in the day after tomorrow's session. So he will be also joining in that session on 1st July. So yeah, thank you everyone. If you I don't see any questions, so yeah, let's
Okay.
end this session. Thanks Anubhav for this joining
Yeah,
to.
no problem. Thank you. Thank you.
Okay, so another announcement is for the talks. So we have a evening session that will be start from in the next 1 hour. So that is from 7 p.m. IST. So let's meet there. Okay. Bye.
Okay. See you. Bye.